AI is pretty much everywhere. It helps us pick movies, get around town, even plays the stock market. It's incredibly powerful. But there's often this huge mystery at its core. We get an answer, but we have no idea how it got there. So let's do this. Let's crack the code on how we're teaching AI to finally explain itself.
Okay, picture this, a really high-stakes situation. An AI is looking at an electrocardiogram, an ECG, and it flags a heart condition that could be life-threatening. And guess what? It's right. But if a doctor turns around and asks, okay, why? What did you see in that ECG that made you say that? Crickets. The AI, it just knows. And, that's just not going to fly. Not when the stakes are this high, in critical fields like medicine or finance or self-driving cars. You can't just base a huge decision on some mysterious black box. We need to see the evidence. We have to understand the reasoning and be able to trust the process, not just the final score.
This right here, this is the heart of what researchers call the black box problem. The AI models we've built are just so incredibly complex, with layer upon layer of calculations, that how they actually think is a complete mystery, even to the people who made them. And this isn't just a tech headache, it's a huge wall blocking any real trust and accountability.
All right, so how do we even begin to peek inside this thing? Well, our investigation kicks off with our very first clue, a really clever technique that's actually built right into some of today's most advanced AIs. It's called an attention mechanism.
The easiest way to think about an attention mechanism is that it's basically the AI showing us where it's looking. Instead of trying to process every single bit of data with equal importance, it learns to give out importance scores. It focuses its brain power, its attention, on the bits of info that are most critical for making the right call. So what does that actually look like in practice? Let's go back to that ECG. The AI goes through and gives an importance score to every single data point in that heartbeat. This essentially creates a heat map showing us, visually, which spikes and dips it thought were the most important. Then it uses that focus view to make its final prediction, which, by the way, often makes it way more accurate.
So, the key thing to remember here is that attention is an inherent clue. It's what's called an anti-hoc method. Fancy term, I know, but all it means is that the explanation is baked right into the process from the get-go. It's part of the AI's thought process, giving us a live look inside the box as it works.
Okay, but what if the AI isn't so helpful? What if it doesn't have one of those built-in attention mechanisms? What if it's a true black box that just won't talk? Well, that's when we have to roll up our sleeves and bring out the detective's toolkit. This method is called feature attribution.
Now, feature attribution is totally different from attention. It's a post hoc technique. That means we use it after the AI has already given us its answer. It's like an investigation where we work backwards to figure out which pieces of the input data had the biggest impact on the final decision.
This diagram here shows a really cool attribution method called integrated gradients. The best way to think about it is like dusting for fingerprints at a crime scene. You start with nothing, a blank slate, and then you slowly add the real data, bit by bit. And with every bit you add, you measure exactly how much it changed the AI's mind. By the end, you have a perfect map of which fingerprints, which data points, were the real culprits.
All right, let's put these two head to head just to make sure we've got it. Attention is built in, anti-hoc. It's part of the AI itself, and it shows us where the AI is looking while it's thinking. Attribution, on the other hand, is applied later, post hoc. It's an external tool that we, the detectives, use to go back and find the clues after the fact. Both super useful, but they answer why at totally different times.
So, we've seen how AIs can leave clues, and we've seen how we can go find them. But what about the next step? What if the AI could just tell us what it did? What if it could write its own report? Well, this brings us to a really fascinating idea, the self-reporting AI.
Well, that's where something called multitask learning, or MTL, comes in. The idea is to train one single AI model to do two jobs at the same time. Job number one, make the prediction, diagnose the ECG. Job number two, generate its own explanation for why it made that diagnosis. It's like a detective who's solving the crime and typing up the case file at the very same time.
And this diagram of the tree really nails how it works. You've got this shared trunk where all the initial data processing happens. Then it splits off into two branches, or heads. One makes the prediction, the other creates the explanation. Because they share all that initial work in the trunk, the whole thing is just incredibly efficient.
Now, it's not perfect. There are definitely challenges. One big one is something called diverging attributions. If you look at this graph, the blue line is the perfect explanation we're aiming for, but the orange and green lines show what can happen. The AI's own explanation can start to drift away from the truth. So the really cutting-edge research right now is all about finding ways to keep the AI honest with itself, to pull those lines back together.
And this quote right here from a recent paper really shows a massive shift in thinking for the whole field. It used to be about building the most powerful model first, and then trying to figure out how to explain it later. Now, people are designing these systems from the ground up with an interpretability-first lens. Explainability isn't an add-on anymore. It's becoming part of the blueprint.
This whole interpretability-first mindset is taking us somewhere really exciting. It's leading to the most advanced idea we've talked about yet. We're moving beyond just finding clues in the data, heat maps and scores, to teaching the AI to think and explain itself using concepts that we can actually get our heads around.
So what on earth does that mean in practice? Well, instead of an AI saying, I flagged this because of data points 90 through 110, it could say something like, I'm predicting a problem because I'm seeing a rapid increase in growth and volatility. See the difference? It's translating that cold, hard math into a language that we can actually understand.
And these aren't just some fuzzy, vague ideas either. Researchers have defined really concrete mathematical concepts for the AI to learn. Things like the overall level or average of the data, the growth or speed it's changing, its periodicity like a repeating pattern, and its local volatility. These are the actual building blocks for a much, much richer, almost human-like explanation.
And check this out, because this is the proof that this whole idea actually works. The solid lines are the concepts the AI has learned on its own, and the dotted lines are the actual real-world values for those concepts. See how closely they track each other? It's amazing. This means the AI's internal dials are directly connected to real ideas, which makes its reasoning totally transparent and allows us to check its work. Okay, so we've wrapped up our investigation into the AI black box. What's the final verdict? Well, we've uncovered a pretty clear path forward, a way to build AI that isn't just ridiculously powerful, but also transparent and, most importantly, trustworthy. Let's just quickly recap the three main paths to an explanation we've uncovered. First, you've got attention, where the AI just shows its work with a heat map. Second, you have attribution, where the detective has to go in and find the clues. And finally, you have the cutting-edge stuff, concept-based models with human-readable dials, where the AI can literally explain its motive. But here's maybe the biggest, most powerful takeaway from all of this. For a long time, everybody thought there was this trade-off. You could have a super accurate AI, or you could have one you could understand, but you couldn't have both. Well, what we're finding out now is that making an AI explainable can actually make it better. They're not enemies, they actually help each other out. And that really brings us to the final and maybe the most important question. As AI gets woven deeper and deeper into our lives, making these huge decisions about our health and our money, being accurate just isn't enough anymore. The real question is shifting from, hey, is it accurate, to something much deeper. Can we actually trust its reasoning? The entire future of AI really hangs on that answer.